it turns out that in order to do this batch of linear algebra that we're about to do, we have to remember some nonlinear algebra from our past. And then specifically, we have to remember how to solve polynomial equations to find the roots of polynomials. In particular, quadratics. And so remembering how to solve a quadratic equation, determine whether its roots are real or complex, that's something that's going to come in handy. Not just handy, but really more or less necessary. And so one of the interesting things about this set of topics that we're going to talk about today is, why does that nonlinear algebra of a single variable show up here? Why do we need to remember polynomials? What do they have to do? What do the solutions of polynomial equations have to do with the geometry of linear transformations? So that's, I hope, going to be one of the sort of pleasant surprises. I hope it's pleasant as we get throughout the rest of the material today. So agenda is, first of all, to come up with a wiser method for computing determinants that's hopefully going to be useful for us, because determinants are going to be sort of essential tools for us as we continue through. Because what we're doing when we measure a determinant is we're measuring how does a linear transformation change the volume, the highest dimensional measurement of size in geometry. Whether that's area for a 2x2 linear transformation, if it's regular volume for 3x3, you might call it hypervolume, or four-dimensional volume for a 4x4 matrix. You get the idea. But today's goal is going to be to take apart those changes in volume to look at how they might have arose from individual changes in the lengths of vectors. And so what we're going to end up wanting to search for are, how do linear transformations change the lengths of vectors that they act upon? And are there vectors whose lengths are being changed by a linear transformation, but whose directions are not being changed by that transformation? So when a transformation changes only magnitude and not direction, we call the vector on which it is acting in that scenario an eigenvector of the linear transformation. And so if we can figure out how eigenvectors' lengths are getting changed by a linear transformation, then if there is a full set of those eigenvectors, in other words, if there is a basis for the domain of my linear transformation consisting of eigenvectors, then the way in which the volume gets changed is going to just be the product of the ways in which all those eigenvectors' lengths are changed. It's like if I have a box and I make it twice as wide and 3 times as tall and 4 times as deep, right? Then I have changed the volume of that box by a total of 2 times 3 times 4 factor, right? Whatever that would be, 24. So to say that the volume changed by a factor of 24 is saying one thing, but to say that the length, width, and height changed by factors of 2, 3, and 4 respectively is saying something more specific, right? And so that's why we're going here today from the general, how do volume changes, that's what determinants tell us, to the more specific, how are lengths changing? And that's going to be what we look at when we study eigenvectors.